is starting working the root locus on the real axis, and then we're going to extend it into other dimensions here. Again, using this one, we'll simply apply is the phase and the magnitude criteria from this. So now the next one is I want to build up the step. We continue from last time. The step 3 is we know for this case, this has a three branches of the root loci. Okay, and the branches basically starting at the poles here, then we're ending up at the zeros. And for this case, apparently the zero determined by the numerator, which has nothing there. But in reality, the zero exists in infinity. So the 3 branches were approaching to infinity in a certain way. So the approaching trend is we want to determine is we call the asymptotes for the root loci, which means we want to know the root loci, each branch of the root loci, how they approaching to the infinity in certain orientations. Okay, so that is this approach we want to determine. So here is to determine okay, and again the asymptote is to help us to visualize how the root, each branch of the root loci approaching to the zero there. The zero locates at infinity. And the asymptotes basically is, here by definition, the asymptote is an approximate descriptions of the root loci. Okay, so approximate description of the root loci, in particular at s approaching to the value infinity there. Okay, so in this case, we're going to approximate the root loci by doing this. So here I simply highlight the keywords approximate and at s approaching to infinity. So in this case, the first one we determine the orientations. Okay, so that means we're going to draw the asymptotes. So before we do the details, I can tell the asymptotes basically is in 60-degree orientation and minus 60 orientation and in 180-degree orientations. Okay, so here I draw is the asymptotes. Here I highlight the orientations and how to do the calculations, and that is here. So by so simply we apply the phase criteria here. So here we calculate for this case. So let me transfer it into this case. 1s, s plus 1, s plus 2 equal to minus 1 over k. Okay. So we consider the informations when s approaching to infinity of this. For this case, let me write it up here. So our phase criteria is this. We know s plus 1, s plus 2 must be equal to minus 180 plus the n L times 360, right? And then for the magnitude, we have is s plus 1, s plus 2 equal to 1 over k. Okay, so here here again, here we consider the case is k is non-negative. Okay, so we apply the phase criteria is s plus 1, and s plus 2. Okay, and by using the phase criteria, that still is minus 180 plus this one. Okay, so that is, before doing that one, this is the phase criteria like this. And right now we want to study the asymptote's behavior, so that means we replace the limit when s approaching to infinity, we see how the orientations being made there. And now for this case, you can see, let me do a little bit derivations here. So now for this case, basically this side, the scratch calculations, this one basically is limit as approaching to infinity. And for that numbers, basically the inside, if you want to expand it, basically is S3 plus 3s2 plus 2s plus, that's it. Okay, so now for this one, you can see when s approaching to infinity, basically the lower order terms will become insignificant. This is a way we can approximate. So here again, we're going to approximate, basically approximate is by dropping off non-significant terms here. So basically this one is approaching to its limit, and simply S3. So this is the roughest approximation, and we take it. Okay. So under this case, then again this one is equal to minus 180 plus L times 360. Okay. So now we can see in this case we do keep the doing calculations. So now for this one we can do this one again. So this one basically the angle of this basically is 3 times the angle of this, right? Do you know why? You should know this one. Is that right? How can we say this one? If you remember our formula there, so say for any complex number, we can express in terms of this format. Okay, so for this number, basically is saying if the point S is here, then the magnitude is sigma, and this phase angle called the theta. So we have an expression like this, right? And then here for S3, basically in our definition we mentioned last time is sigma 3 times Ej times 3 theta. Okay, so that is from the previous definition. So from here you can see when this has a the multiplicity of the index 3, so basically that phase angle is increased by the multiple numbers. So from here, basically here, this is equivalent is minus the phase angle of 1 minus phase angle of S3. So that is the minus phase angle of S3, right? So that one, using this concept, is minus 3 times this one. Be good? Okay, so we apply that concept to here. So using this case, basically this is a limit as approaching to infinity 3 minus 3 times this angle of S. Okay? And this one equal to minus 80 plus L times 360 degrees. So again, let me continue to do the calculation here. So basically the right hand side is limit as approaching to infinity times angle S equal to, I divide by minus 3 on the both sides, so that is minus 180 degrees plus L times 360 divided by minus 3 here. Right? I simply remove the minus 3 to that sense. So here we do the implementation. this one can be equal to, say, when L equal to 0, then this one is 60 degrees. And when L equal to, say, minus 1, and L minus 1, and this is minus 540. 540 divided by this is minus 80 degrees. Okay? When L equal to 1, so that is 360 plus this one, so that is minus 60. Okay? And we keep going. So when L equal to 2, then you will find the 3 number will begin to cycle. Okay, so basically here, that is the one we need. We don't need to repeat fully. So that's the reason we have 3 branches. This is the, what is this? This meaning the orientations of the S. The S is on the root loci. So that means the orientation of the root loci when approaching to infinity. So basically this word simply is saying the asymptotes. Asymptotes simply describe it by this description. You good? Okay, so that means here for asymptotes, the orientation is the 3 numbers. And simply we can't really graphically, we simply highlight. When you plot it, you better plot it in a good way. Okay, so basically this one is 60 degrees. And this orientation is minus 60 degrees. And this orientation is in 180. Okay, minus 180. Minus 180 is simply is measured from here, the same. Okay, pointing to there. Any questions about this? Good? Okay. So this is to determine the orientations of the asymptotes. Then the next one, the second part is we want to determine the intersections of the asymptotes. Okay, so the asymptotes, each asymptote is a straight line. The 3 straight lines will intersect at one point there. So we want to determine their intersections in the way to better plot the asymptotes. Okay, so that is our second task here. So let me put this one here. So the second one is the intersections. The asymptote intersections can be determined by this. This was still starting from our base angle criteria here. And this is minus 180 plus L times 360. And here we want to study the asymptotes. So here we put this notation in the way that is we study this behavior. Okay. And compared to the previous one, for this we will use the beta approximations for this case. For this one, again, here is the calculations. So for these terms, we still do the approximations, and this time we do a beta approximations. So this is this case, and let me write it up here. So this is the equal to S3 plus 3S squared plus 2S, okay? And again, I copied this one. So right now it's identical, nothing approximate yet. So the next one, I want to do the approximation is this. Compared to this case, we only pick up the first term and dropping off these remaining terms. For this case, I want to pick up the first 2 terms for beta approximations. Okay. And with the first 2 terms, that will allow us to come up with a complete form like this. With the information as the first 2 terms, if we want to make up this form, okay, so if we want to make up this form such that the first 2 terms will be appearing like this, then that would be possible way is s plus 1. Because after you expand this term, then compared to this, the first two terms will be identical, although the remaining terms will be different, right? So here we do the approximations. Okay, and with this technique, we'll be able to find the intersections, and that'll be shown in the remaining. Okay, so here is the S. We still copy this. Okay. So this one, again, this one is equal to minus 180 degrees and plus L times 360 degrees. We copy from the right-hand side here. With this information, again, this one, what is this? This case, again, I erase it. This one basically is, for this angle, simply is the, let me do it from the beginning. That is the phase angle of the numerators minus the phase angle of the denominators. Right? So let me do the detailed calculation just for this term. So this one is 0 degrees. Okay? And this one, again, borrow our previous concept I erased here. So that's the 3 times of the phase angle of s plus 1. Be good? Okay. So basically this one simply is minus 3 times s plus 1 here. Okay. So keeping those things in mind, then let me borrow a few space in here. So we continue our calculation. So right now, let me plug into there. So limit s approaching to infinity and times minus 3 of s plus 1 equal to minus 180 plus L times 360 degrees here. Okay. So again, here let me divide both things by minus 3. So limit s approaching to infinity s plus 1 and equal to minus 180 plus L 360 and divide by minus 3. Okay. So again, from here you can see this is a better approximation than the previous one, and then we can figure out how can utilize this one to find out the intersections. So now for this case, S, right now this expression is from our derivation. We have a better approximations, and our effort is to try to find the intersections of the 3 asymptotes. So here we're assuming S will be equal to sigma plus j omega. So basically what is S? S is because of these expressions here. Because here we use this notation, basically S is the point the asymptotes. Okay, so S could be our root loci, but for sure S is the collection of the point on the asymptotes. Asymptotes is a better approximation to the root loci. In this step, our focus is on the asymptotes. Okay, so as long as we can figure out the relation between sigma and omega, so this is sigma, this is omega. So basically we have the relation basically the straight line. Okay, so we start with here. So now with this one, then that will be equal to, for this case, let me plug in. By plugging sigma s equal to sigma plus j omega, that is s, and then plus 1. Okay, and that one will be equal to, on this side, the case will be equal to, from here we already have done that one. This could be have 3 values, minus 60 degrees, 60 degrees, and 180 degrees, right? Okay, so the right-hand side here we have done earlier in the previous step. So here I simply copy the result here. So we have this formula. So what is this? This is the angle. Angle basically is arctangent. What is that one? And omega sigma plus 1, right? Do you remember? So if we have any number here, so S equal to A plus JB, then phase angle basically is we're using this. So that means this is the real part, this is imaginary part. So this phase angle theta equal to arctangent, the imaginary part divided by real part. So for this case, this is the imaginary part and this is the real part. So we pick up this formula here. Okay. So now for this case, we keep doing here. So now with that information, so therefore omega sigma plus 1 have three possibilities: tangent 60 degrees, tangent minus 60 degrees, and then the tangent 180 degrees, right? Okay. So with this case, that means this one will be equal to 60 degrees is is that right?
Yeah. Here you have negative 60 to 6180, and then you flip the sign.
Oh, that's okay. Doesn't matter. Okay. So that is this one, right? Good. Okay. Why I think I have a mistake here, but anyhow we keep doing. So this one is how much? Minus 2. This is minus square 3, and this is square 3, and 180. This is 180 is how much? 0. Okay. So here we have the possibility. That means omega. So therefore, that is this omega sigma plus 1 minus omega square 3 equal to 0. Sigma plus 1 plus omega square 3 equal to 0. And then here is omega equal to 0. So we have three equations. You good? You simply solving this equation with the three numbers, and then we have these. Each of the equations is a straight line in the complex plane for one asymptote Okay, so let me draw it. The real part is sigma, and imaginary part is omega. So for this case, maybe we can do this one here. So here, this is the sigma omega. So for the first one, that is so say sigma plus 1 minus omega equal to 3 equal to 0. So when sigma equal to sigma omega, when this one equal to 0, then omega will be equal to square 3. When omega equal to 0, sigma will be minus 1. So here that is minus 1 minus 2. So one section, one point will be here, the other point will be here. So this line representing is this straight line. Right? So right now I'm trying to draw this straight line equation. If you try to imagine this is x and omega is y, right? So we can draw this straight line. So that one we can plot here. Asymptote is this. So going through minus 1, so that is here. Okay, so this is the asymptote. Asymptote, that is the behavior to approximate the trend of the root loci. And then you can repeat for the second equation here. So for the second equations, and sigma plus 1 plus omega divided by 3 equal to 0, you can quickly plot this one. Basically, that line is this one. Okay, intersection is minus square 3 here. Okay, so we can plot the the second one that is here. So try to make a good scale, so that should be here. Okay. So basically this is a 60 minus 60 degrees and 60 degrees. 60. Okay. And then the third one simply is this. So the blue line representing is the asymptotes of the root loci. So basically, eventually, when s approaching infinity, the root loci will be basically converged onto the asymptotes. So here I can just be good, feel good. I can say, okay, eventually the root loci will be on there. Good. So we fix the starting point. Then at the end of this step, we fix the ending point, the ending of the root loci. And now we're going to work on the transitions. So what is the root loci in between from the k equal to 0 to k equal to infinity? Okay. So that is our step. Good? So start, we can have a new section.